green sheet. Let's see where we left off at. I'll return to quizzes at the end of class today. Please remind me. Any questions about lab today or this week? Okay, let's see where we left off at. Gabriel synthesis. Gabriel synthesis is the way to make primary amines. Yes, primary amines. The product of this reaction here, potassium thioimide, followed by hydrolysis. Make that primary amine. How do we do? Question? Good question. Acidic conditions, it should be protonated. Yeah. This is going to require some type of basic workup. You're exactly right. Yeah. You'd have to have some type of suitable workup. Okay, often that's glossed over. But the neutral form would be the amine. Okay. Next, dehydration of primary amides. What can you do with amides? Well, amides typically are end products. Amides can be hydrolyzed back to the carboxylic acid. We showed that. If you have an imide with two carbonyls, you can hydrolyze both carbonyls off and you can generate a primary amine. That's the Gabriel synthesis for making primary amines using the anion of like thioimide. One unique reaction you can do with amides is you can dehydrate them to the nitrile. Primary amides can be dehydrated to the nitrile. You take this primary amide, you get the nitrile. We have lost water. Okay? If you just look at formula, we have lost water, so we can call it a dehydration. But of course, we're going to have to use some reagents here, and we're not going to just produce water. This is just sort of formally, or essentially, what we're removing. This can also be done. This can be done with thionyl chloride. It can also be done with acetic anhydride. I sent a mechanism. The next few reactions I sent by email. I'll make some brief comments here and then see if there's any questions. With the amide, the first thing is remember the key resonance structure, where we put the anion on oxygen, and the electrons are moving towards the oxygen. Remember when we showed a NMR of such a resonance structure? It had two methyls, and the methyls were not equivalent, indicated there. But from here, the oxygen of the amide is pretty nucleophilic. Attack the sulfur, electrons upright. Okay? Then they can come back down, kick off the chlorine. That'll lead you to this here. The chlorine can take an H, that does produce HCl. We ultimately produce two HCl's. Right here we produce one to get this structure. Now, anytime you make a pi bond using a lone pair, kick off a leaving group, that's easy to do. This is a lot like a tosylate. We've seen this oxygen leave before. That gives, what are we trying to accomplish? We're trying to get a triple bond between the C and the N. Well, right here, a triple bond between C and the N. It's there. There's an H remaining. Here's the leaving group. It's going to collapse and lose Cl minus, SO2 Cl minus. The Cl minus takes the remaining H, and you produce the second HCl. It's an interesting reaction. You may not have ever would have imagined this. Hopefully when you see the mechanism, it looks pretty straightforward. Some basic concepts we've been doing. And this is a common reaction of primary amides, to dehydrate them, to essentially remove H2O to make the nitrile. And so the carbonyl carbon, it used to be that there. Any questions about this mechanism? So we're essentially dehydrating the primary amide to the nitrile. This is a way to make nitriles. Of course, the other common way to make nitriles is to take something like this and react it with like sodium cyanide and just do an SN2, because the cyanide is such a common nucleophile that you can purchase and do SN2. Okay, the next side of the green is what chemistry of nitriles. Well, how do you synthesize them? Well, we just showed it on the previous page. Use cyanide or dehydration of primary amide. Okay, B, what can you do with nitriles? Nitriles tend to be final products. There are miscellaneous things you can do. For us right now, about the only thing you can do with them is hydrolyze them back to the carboxylic acid. A nitrile is a carboxylic acid derivative. We introduced it very early on. The carbon has 3 bonds to a more electronegative atom, the same as the carboxylic acid. We can hydrolyze back to the carboxylic acid. Not with pure water, but either with acidic water or basic water. This would be an acidic hydrolysis. And we're adding water to the nitrile. When you add water to a nitrile, what do you get first? The amide, which is just the opposite of what we did, because what did we do on the previous page? We went this way, right? We removed water. If you remove water, you get the nitrile. If you add water, you get the amide. The amide is the first intermediate, or the intermediate here when you add water. But then we can add water again, and we can hydrolyze off the nitrogen, and we can get the carboxylic acid. Typically, this reaction is difficult to stop here. In brackets means it's not isolated, but it just continues on. And so we can go all the way. We've already seen this mechanism. It's just good old protonate. Water adds up, down, kick off the nitrogen. Make sure you keep track of the proton. Use it as you should. Mechanism for this acidic hydrolysis. It's really not a hydrolysis because we're not lysing anything, but it's generally called a hydrolysis. So the sheet. So when we get to the chemistry of nitriles, under acidic conditions, we can protonate the nitriles just like protonating a carbonyl. By the way, did we cover protonation of carbonyls? I need to make sure we covered that because based on the quiz, it doesn't seem like we covered it. Which handout is that in? Chemistry of acid derivatives. General concept, the one with the chart or the diagram where I fill in all the lines. That one there, right? General concept, protonation of carbonyl makes it more reactive. Okay? Protonate carbonyl. And then we can start having nucleophiles add to carbonyl. Typically, if you're doing carbonyl chemistry under acidic conditions, the first thing you want to do is protonate the carbonyl. Okay? Well, with nitrile, it's the same thing. We're under acidic conditions. We can protonate the nitrile. Protonated nitrile. You want to consider this a carbonyl, but this makes the nitrogen more electron demanding, more electronegative. It's like, I need some electrons now, so it pulls harder. You create a larger dipole. The carbon is now more electropositive or more electrophilic. Now the weak nucleophile water will add, where typically it will not add to a unprotonated nitrile. You have to have acidic conditions to get the water to add. It's now more electrophilic. Water adds. You should be able to follow these arrows, right? Electrons over, this gives this. What are we trying to accomplish? We're trying to get to this structure. So now we have a carbon O single bond. We've got to make this a double bond. We've got to get rid of these H's because there's no H's on the O, right? When you do a mechanism, you got to see where you're going. But then take it one step at a time, right? We do proton transfer. We got an acidic H on oxygen. Let's put it on nitrogen. Proton transfer. Now you can actually do resonance. Anytime you have charges, pi system, always consider resonance. So I'm showing a resonance structure. And when I show resonance, wow, look at there. It's product except it's got an H on the carbonyl. So we just take the H off using whatever was the anion that gave the H up. And there you go. There's your amide by adding water to the nitrile. And we've already done the subsequent hydrolysis where you would just protonate. If you were going to just do this all together, instead of taking the H off, you wouldn't want to do that. You would just bring in water, electrons up, transfer the proton to the nitrogen, back down, kick off the ammonium, and make your way to the carboxylic acid. Now you can also hydrolyze the nitrile using hydroxide. Now actually with hydroxide, I've recognized that hydroxide is actually a catalyst here. And you actually need an equivalent of water. Here, we don't have a proton to protonate the nitrile, right? But we have a stronger nucleophile. We have the anion version of water. Stronger nucleophile will add. Typically it requires heat. What does that give? Here. We want to get H's on the nitrogen. Well, this is an anion. Take an H from water. Water can be a proton source. Not acid. We don't have any acid here. Not hydroxide. Water is present. How is water present? Well, like I said, you got to have water. That gives us this here. Hydroxide can take this H off. We are looking to get H's off of the oxygen. Now we can do resonance, and that gives this structure, which is basically our final product, except we want to put an H back on. And water can supply the proton, and that gives us here, but we regenerate hydroxide. So actually hydroxide is a catalyst here. Note a difference in the mechanisms. Under acidic conditions, all of your intermediates are positively charged. Top, positive, 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 positive. Under basic conditions, all your intermediates are negative or neutral. I mean, that's neutral. You can have, okay, but that's very typical. Under acidic conditions, most of your intermediates are positively charged. Under basic conditions, typically negatively charged. Go look back at the past mechanisms from the past 3 tests. You'll see that. You're not going to protonate something and have a positive charge under basic conditions. There's no proton source. Water will not protonate a neutral, but it will protonate an anion. Any questions about those two hydrolyses of nitriles? We'll see a little bit more chemistry of nitriles on the next handout. At this point, it's getting to be sort of just basic arrow movement, and if you know how to move the arrows, then you just kind of see, okay, I see what's going on here. And of course, all roads lead back to carboxylic acids. Nitriles can be hydrolyzed, right? Comes over here, right? Anything in the box, including nitriles, can be hydrolyzed back to the carboxylic acid with base or acid. Of course, if you're under basic conditions, it's going to exist in the basic form. you want to put the H on, you got to treat it with acid to go back up to the neutral carboxylic acid. Okay, questions about the handout, email? Okay, let's finish up the green sheet, a couple of miscellaneous things, including also polymers. First off, what's the name of this guy? Carbonic acid. Carbonic acid, carbonyl with two OHs. Okay? This is not a carboxylic acid derivative. How many bonds to a more electronegative atom does the carbon have? 4. It's more than 3. It's not a carboxylic acid derivative. It's a carbonic acid derivative. Now, carbonic acid is not stable. It decomposes to water and CO2. This is why when you treat baking soda with vinegar, it bubbles up. It's CO2 coming out. We'll see it a little bit below. Now, you can also have derivatives of this. Your monoacid derivatives, like it looks like an acid on one side and on the other, these are not stable either. These will typically lose water, lose CO2. Basically, mechanistically, these electrons come in here and this gets kicked off. Now, it could be self-protonated, so you're kicking off ammonia, CO2 and ammonia. So that's not stable either. However, there are some things here that are stable. The diesters are stable. And that's called diethyl carbonate. Carbonic acid, diethyl carbonate. The dichloride is stable. It may not look like it is. It's very reactive. The dichloride is called phosgene. Very reactive. Nucleophiles would love to add here. Very reactive, very toxic. One of the James Bond movies, I think it was You Only Live Twice, Mr. Bond. They were in a cave, and then they were like, "Quick, get out, phosgene!" The bad guys had gassed the cave with phosgene. It's a gas, and it's very reactive. You don't want to be breathing this stuff. So they mentioned that. The diamide is stable. Anybody know the name of the diamide? Urea. Yeah? It's a carbonic acid derivative. You can have mixed derivatives, ethyl carbamate. Okay. Typically, though, when you have an OH, it's not stable because it'll lose CO2 and kick that other thing off. The salts. Well, if that was H, that'd be carbonic acid, but this is the monosodium salt of carbonic acid. We call it sodium bicarbonate, right? This is disodium, right? That's carbonate. It's the dianion of carbonic acid. And you can have sodium carbonate, potassium carbonate, or if one of these remains the H, you have this here, and you can have sodium bicarbonate, etc. The anions are stable at room temperature, okay? But baking soda, there it is, baking soda. You treat this with acetic acid, vinegar, well, that's acidic. And so this takes the H. And what do you produce? Carbonic acid. But it's not stable. The carbonic acid that's formed then breaks down to CO2 and water. The CO2 bubbles out. Now these guys will decompose at high temperature. If you heat this up to like 500 degrees, it'll kick off this hydroxide and give CO2 and hydroxide. But at normal temperatures, the anions are stable. So these are all carbonic acid derivatives. Next thing, let's take a look at a very important miscellaneous topic, condensation polymers. Okay, this is the hydrolysis product of caprolactam. It's an amino acid with the amine way out here. We might be able to cyclize this, like on the quiz, by the way. You'll have it on your quiz, you may not need to write it, but if we take this plus maybe this amine, methylamine, what type of product can you envision maybe trying to be made here? Now, a number of you drew it on the exam, on the quiz, maybe trying to make the amide. Okay, plus what? If this worked and you fully balanced it, plus what? Plus water. Yes. So these two would react to give the amide and give off water. That would be called a condensation reaction, when it gives off water. Problem is, we know that this doesn't happen. Instead, what happens? This takes the H, yeah? And you're just going to make the salt. Okay? But if this was to attack and make the amide, you'd give plus water. You'd lose the water, but I put it in quotation. That requires some type of activation. If you don't have any activation, you're just going to do a proton transfer. But this is still a theoretical outcome, a condensation reaction. But look at this guy. This guy can also self-react. What if this end reacted with the acid and made an amide, and this end reacted with the amine and made the same amide? You could make this repeating polymer. Nitrogen is now bound to carbonyl through a condensation reaction, and carbonyl is now bound to the nitrogen. So it's just the same thing. That's a repeating polymer, and that is nylon 6. It's like stockings were made of. The 6 referring to the number of carbons. You could have less carbons if you like nylon 5, but nylon 6 is the most common. This is a homopolymer, because one starting material led to the polymer through a condensation reaction. How this happens? Well, it requires certain reagents. We know that it doesn't happen directly, because directly you're just going to get proton transfer. But theoretically it can, and we can call it a condensation reaction. There are other condensation polymers. Kevlar, which is used to make like bulletproof vests. Here's the structure here. It's called a polyaramide. Poly meaning multiple, aramide. Well, it's an amide, but it also has the aromatic ring. So aromatic amide, aramide, sort of shortened. Can you do this? Now this is a copolymer. That means there's 2 different molecules, or sometimes even more. But at least 2 different here. Can you show the 2 molecules that would react by a condensation polymerization to give Kevlar? These two condense to give the amide. By the way, that's called phthalic acid. This is just a diamine. And so this condensed to give the amide. And then the other amine condensed to give an amide. You see, just keep on going, right? And then you say, okay, what's the repeating unit? As drawn there, let's say here. Carbonyl, NH, boom, boom, and then do it again. Now hold on, we need 2 rings because if I went here, carbonyl, NH, ring, N, carbonyl, N, that's not repeating until we get here. There's 1 repeating unit. Carbonyl NH ring, N carbonyl ring. Carbonyl NH ring, N carbonyl ring. So it's actually, the repeating unit is actually kind of long. It's a copolymer because 2 different molecules. Okay? But each of these amides was formed from the condensation of the amine with the carboxylic acid to produce water. Again, it requires some type of reagent to activate this. Okay? I'm not showing that. Kevlar, lots of hydrogen bonding, holding Kevlar together, making it very strong and nearly impenetrable. Hydrogen bonding. You can actually make Kevlar thread. What's below? So up top, the Kevlar is a polyamide. What are these down here? Those are polyesters. Ever heard of polyester? Of course you have, right? Okay. But there's some more sophisticated ones, some that are stronger than the original cheap polyester, or, okay, like Dacron, Durastar. Some of these are made, I think Durastar, when I founded it, they said plastics. Okay. Some polyesters can actually be plastics as opposed to more cloth-like. And they were seeing how, like, the plastic seats at some of the football stadiums that you sit in, you know, these are cloth, but made of Durastar. Okay. One thing, can you show the monomers that need to be reacted to form these polymers? They're copolymers. Both of these are copolymers. Yeah. So think about being able to show the monomers that are needed to react to form these. One of the ultimate polymers is proteins in your body. Proteins. These are actually polymers that come from polymerization of alpha amino acids. And of course, this would be more than a copolymer. I mean, you've got multiple. You've got 20 different building blocks. But all these could come together and make a big polymeric chain called a protein through a condensation reaction, ultimately. Any questions about polymerization? Homopolymers, copolymers. Identifying the monomers that go into making the polymer. It's actually very practical stuff there, yeah? Putting organic chemistry to use, and a lot of people make a lot of money. Yeah? New polymers. Okay, next handout. Test of the week from today, yeah? Our next handout, I sent by email, but I'll also give it to you here. There's a nice warm-up question there. So let's go ahead and start over here. With this handout, we're going to start moving into aldehyde ketone chemistry. Okay? And when we get to test 4, that will be predominantly aldehyde ketone chemistry. But some here on test 3 as well. Okay, this is presented, so just let's look at these reactions. Okay, there's no text description here. We're looking at it, reaction. Ketone here, obviously, yeah. Sodium borohydride. I don't think we've seen that this semester, but we saw it organic 1 in the oxymercuration, followed by the sodium borohydride sort of step. What sodium borohydride is a source of what?
Hydrogen.
Well, in what form? Hydride. H minus source. Hydride. We don't often see hydride. Yes, it can exist. I mean, sodium hydride is very common. Na plus, H minus. And for the H3 minus, it has 2 lone pairs. Sodium hydride. Sodium hydride is not useful, though, for these reactions. These two, which are both H minus sources, are much more versatile for the chemistry we're going to be doing. Sodium borohydride, we have a boron with 4 H's. What's the charge of the boron? Negative. We have a sodium that sits with it, sodium borohydride. Boron has 3 electrons, right? How many does it have here? 4. It has 4 valence electrons there, that's why it's an anion. Sodium borohydride. Okay, you can't ever make boron happy. It either doesn't have enough or it's got too many. Well, okay? Well, here it's got too many electrons. It's like, I got too many, I want to get. It's like, H, you and your 2 electrons, go. I don't want you anymore. So it kind of shoots them out. The H and the 2 electrons. And so it's like a H minus darts or something being shot out from the boron. The H and the 2 electrons. Okay? We're just going to call it as an H minus. Well, like we did Grignard's, it reacts as an R minus. Essentially, this is H minus source. So is lithium aluminum hydride. That's Al with 4 H's. What's the charge of the aluminum? Well, it's under boron. It's the same electron considerations. Negative. Lithium. Lithium just happens to be more common with the aluminum. Yes, you can buy sodium aluminum hydride, but lithium is by far most common. I'm not sure why, but it is. A lot of times this is shortened to LAH. LAX is airport in LA. This is LAH. You ever hear LAH? That's what we're talking about. Okay, H minus. Here we go. What's it going to do? H minus can act as a nucleophile. Acid carbonyl. Electrons up. And we get what? We get that.
With the H.
Yeah, there's an H there. See it? I don't usually draw in H's. Do y'all draw in H's usually? It's there. Because if it wasn't there, there should be a charge there. There's an H there. I mean, do you want me to draw it in for you? But we usually don't draw in H's. And since the beginning of Organic 1, keeping track of the H's has always been something very important. And if you've not been doing that, I suspect it's been giving you trouble along the way. There you go. We just made that bond, right? H minus N, electrons up. What do we do now?
Electrons back down.
Electron, kick off the methyl? No. Plain carbon's not going to leave.
Kick off the
Now, I know we said easy to kick it off. And we would see you could even have a carbon, but a plain carbon's not going to leave, a hydrogen's not going to leave, and the phenol's not going to leave. There's no leaving group here. This is not an acid derivative. It's aldehyde ketones, which do not have like a heteroatom.
But we got the soda.
This is it. Game over.
But the soda.
The only thing you can do is some type of H plus source or workup. And this just picks up a proton and there's your product. With aldehydes and ketones, you do not reform the carbonyl. Unless it's going to be a unique reaction where we say, hey, this will get kicked off. But plain groups like phenols and hydrogens and carbons and ethyls and propyls ain't going to get kicked off. So all we did was just nucleophilic addition. And we did not do an elimination. It's just aldehyde ketone. And that's it. So the ketone was converted to that alcohol. And yes, there is an H there on that carbon. Now, where can the H plus come from? Sometimes like ethanol solvent. But you can only do that with sodium borohydride. LAH you can't use alcohol solvent. We'll talk about that maybe a little bit later. Look at the product we made. Question over here. What reagent would convert product back to starting material? Huh. What reagent would convert product back over here? What type of reaction is, if we go this way?
Oxidation.
Oxidation of the alcohol to the carbonyl? Have we ever done that before? Yes. One of the big three would oxidize that. So what are we doing here? Going this way, if this is an oxidation, what is going that way called? Reduction. How do you tell if you're doing a reduction? Adding H's? Yeah, that's what we added. You see it right here? We added an H. We reduced the ketone to the alcohol. We added H's. And if you come backwards, you're removing H's. You're doing oxidation. This is your old redox cycle of aldehydes, carbonyls and alcohols. This was test one. Going that way. Coming this way, we're doing now, and it's most typically done using a hydride source. As you flip over, you'll see this redox cycle illustrated with estrogens, estradiol versus estrone. And what's going on here? When you go to estrone, the secondary alcohol is being oxidized to the ketone. And that's why it's called estrone, ketone. But you can also come back and you can reduce the ketone back to the alcohol. Okay? Now your body doesn't use the big three, your body uses an enzyme such as NAD+. To come back this way, your body doesn't use sodium borohydride, it uses like NADH, NADPH. That's the redox cycle of going between carbonyl compounds and alcohols. So, show the product of the next reaction, number 2. Anybody have it? I recommend thinking mechanistically, do mechanism, then here's your product. Get that alcohol right there. Now, assume excess reagent and aqueous workup. Aqueous workup. If you do aqueous workup, that's going to supply the proton that's needed. Everybody get that alcohol? Of course, mechanistically, what do we do? Add it there, boom, boom, boom. Electrons up, became minus. If you want to keep track of the H's, please do. There's 2 there now, right? 1 was drawn in. We now have a new one here. Where's the H going to come from? Like we said, if you do aqueous workup, that'll supply the H. Then this takes the H, and there you go. Now, just because I drew this bond down doesn't mean you can draw it up. And there are 2 H's here, right? I mean, everything's there. So we reduce the aldehyde. Question. Same answer over there. The one below we'll need to look at. How about down here? Huh? You should be able to do this one.
It shouldn't be the same answer, right? Because that would yield. Yeah, it would yield
Secondary, so you need tolerance.
So we got to use PCC.
Good. I just making sure you're overweight. Let's look at it. What reagent would convert product back to starting material? You're right. If we use big 3, we get carboxylic acid. Very good. So what would you want to use to get aldehyde?
Collins.
Oh, yeah, you can
Or
PCC. Not Tollens. Tollens oxidizes aldehydes to acids. Yeah, very good. Big 3 would take it to the carboxylic acid. It is an oxidation, though. Okay. How about down here? Huh?
Oh, right.
I shouldn't have to tell you what to do down there. Show the product. By the way, before I erase this completely, which is a stronger hydride source? And the cation really doesn't apply too much. Which is a stronger hydride source? Bore hydride or aluminum hydride?
Well, because it wants to pick up the water.
Why bore hydride?
Or like
Which one's stronger?
LAH,
Yes, why?
because it's going to hang on to its H's less tightly than
Why?
boron would, because they're electron
It's not
sources, and boron is more electronegative than
Boron's more electronegative. Which one hates the minus charge the most?
aluminum.
Aluminum hates it the most. Boron's more electronegative. It handles it better than... Yeah. Aluminum is really mad. It'll give anything hydride. Take my hydride and it'll be reacting with lots of things. LEH. And LEH you can't use in alcohols because the hydride will take the H from the alcohol. So for hydride though you can't use in alcohols. And if you use an alcohol, it can supply the proton in these reactions. Okay, Grignards you can't use in alcohols. But what is this? This is really this, right? Okay? Boom. Electrons up. Boom, boom, boom. Electrons up. Phenyl. This is just going to pick up an H and work up. There's your product. What happened to the H? Nothing happened to it. That H is right here. I just didn't draw it in. I usually only draw in my H's with aldehydes. And that H is here. Which bond did we make? There. Electrons up. Where did that H come from? Workup, some type of workup. It didn't come from anything here. It had to come from like when you had it in water. There you go, nucleophilic addition to carbonyl. The O picks up an H. By the way, you remember when we did epoxides? What type of product does epoxides give when it reacts with nucleophile? Nucleophile, carbon, carbon OH. These reactions give nucleophile carbon OH. Nucleophile carbon OH. Same, the two of above is the same thing because the nucleophile was an H. Because that used to be a carbonyl. Nucleophile carbon OH. Question over there. For number 3, is the product RS? It is chiral, you see. Is it RS? Well, it has to be both, because if it was just S, you'd get a Nobel Prize, because you can't make something that's optically active if these are not optically active. And they're not.
Oh.
Racemic. Why is it racemic?
Because they can attack.
Your carbonyl is planar. The reagent can attack from the front or back. That is... This can be bolded or dashed. I'm not going to go into this any further, but it has to be racemic. You can't make an RNS product here because nothing over there is optically active. It is chiral, it's going to be racemic. If the phenyl attacks from this side, it pushes the O back. Or it attacks from this side and pushes the O forward. It's a 50-50 chance. It's going to be racemic. Same thing with the number 1. If you look at it, number 1 was a chiral product. It's also racemic. Okay, going backwards here. This is a good place to end. Synthesis. Give 3 different syntheses of this, starting with a carbonyl compound. One-step syntheses of this, starting with a carbonyl compound. There's 3 different carbonyl compounds you can start with. Show all 3, and then show what you would react them with. Okay? Please do that. Let's move ahead though. Now let's work on that. Let's try one more before we end. Just to get you started, please be looking ahead at these. Please be looking ahead. Let's try this one here. What's this a source of? H minus? Check. Here, electrons up. What does that do? Give that right there. Nucleophilic addition, hydride to the acid chloride, right? Is game over here, or can something happen here? Here we have this is an acid derivative. It's got an X group that can leave. Oxygen, nitrogen, all these can leave here. What's this going to do? Yes. And what's going to be the product? Aldehyde? Do an acyl substitution, addition elimination. Well, guess what? You're not going to be able to stop here. Hydride will react again. You're not going to be able to stop here because we know hydride reacts with aldehydes. Refer to number 2 above. You cannot stop at the aldehyde. If you want to stop at the aldehyde, you have to use dibol. We'll pick up there on Wednesday what dibol is. Okay?